So in the last video, we have discussed generalized na pigeonhole principle, and it may be expressed in this formula. The ceiling of n over k equals r given n and k. So we use this formula to find r, or the minimum number of pigeons that can be placed in at least one of the boxes. So there are also some problems wherein we are also concerned with the n. So given the k and the r, so we must find the n. So n is the maximum number of items that can be placed into the R boxes, with a restriction that no more than k items can be placed into any box. So we can understand it better with this illustration. So how many possible pigeons are there to ensure that there's at least 3 pigeons in one of the pigeonholes? So for example, how can we ensure that this pigeonhole can have at least 3 pigeons? Okay, so just at least one of these pigeonholes should have at least 3 pigeons. Okay, so or maybe we can have a different placement. This also satisfies the restriction that there's at least one pigeonhole, that there's at least 3 pigeons. Okay, so anyway, let's have some example. What would be the minimum number of students required in a discrete mathematics na class to be sure that at least 6 will receive the same grade if there are 5 possible grades A, B, C, D, and F? So the number of pigeonholes will be the 5 boxes A, B, C, D, and F. So what would be the number of pigeons? So that would be the number of the students. And our problem would be to find the n such that the ceiling of n over 5 is equal to 6, or that given 5 possible grades A, B, C, D, and F, what would be the minimum number of students n in order to ensure that there will be at least 6 to receive the same grade? Okay, so we can visualize it like this. Suppose we have the 6 na students who have the same A in a grade, or maybe these 6 na students could have B in a grade, or another na 6 na students that will have B in a grade, etc. Okay, so let's dive into the solution already. So we use the generalized na formula ceiling of n over k. So substituting our values, we have the ceiling of n over 5 equals 6. So the n over k must have, or is restricted into this domain. The ceiling of n over 5 must be less than or equal to r. So in this case, our r will be the 6, and must be greater than r minus 1. So you can think of it like this. So we have the 6, the ceiling, right? The in which at least 6 will receive the same grade, correct? And then the r minus 1 will be 5, but we are not including the 5 here because the 5 is the ceiling of another from 4 to and with additional fractions. Okay, so our range would be that the n over k will be between r minus 1 and r, but not including the value of r minus 1. Okay, so in this case, substituting 5, so we have n over 5 must be greater than 5, or must be less than or equal to 6. Okay, so given this range, how can we find the n? So we simply have to multiply this whole equation by 5. So we have 5 times 5, n, and greater than 5 times 5, and less than or equal to 6 times 5. So equating it, we have the n greater than 25 and less than or equal to 30. So this is the range of n, or the range of the number of students that is required in a discrete math class to be sure that at least 6 will receive the same grade. Now, what we were asking for is the minimum number of students. So what we need is an integer. So what is the minimum number of students given this range? Okay, so 25 is not included, and is greater than 25. So it should be 26, correct? Pasok siya sa range. So 26 is greater than 25. Tama? And also less than or equal to 30. Now, what we did is we simply added 1 to 25, correct? So what we did here is we can use this final equation n equals k times r minus 1 plus 1. So how did we get this equation? So going back to this range, so we have k times r minus 1, k times r minus 1, and then we just have to add 1. Okay, so 25 plus 1, so that will give us is 26. All right, so yeah. So generally, through the pigeonhole principle, we have n equals 5 times 5 plus 1, which is equal to 26. Right? So here's the formal definition. When we have n objects, the generalized pigeonhole principle tells us that there must be at least r objects in one of the boxes as long as we satisfy this inequality, the ceiling of n over k greater than or equal to r, and that n over k is greater than r minus 1. So we can put it simply mathematically as this. So we have the n over k, it must be between r as the ceiling and r minus 1. So you can think of it like this. So for example, your n over k results to 2.5. Okay, so the ceiling of 2.5 is 3. So the ceiling of 2.1 is 3, right? So the n over k must be between r and r minus 1, but not including r minus 1. So yung r minus 1, this 2, is the ceiling of 1 point, etc. 1 and plus a fraction. Okay, so the smallest integer n with n over k greater than r minus 1, so what we are looking for is here, would be n is equal to, multiplying this part, k times r minus 1 plus 1. And that would be the smallest integer satisfying the inequality, the ceiling of n over k greater than or equal to r. Okay, so let's have one more example. Assume that there is a standard deck of 52 cards. How many cards must be selected to guarantee that at least 3 cards of the same suit are chosen? So essentially, we must find the pigeonholes as well as the pigeons. So the pigeonholes will be the suits, and the 4 suits that are the spades, hearts, clubs, as well as the diamonds. And then the number of pigeons will be the number of selections or the number of cards that will be selected. So what we want to find is to find this n to guarantee that at least 3 na selected cards will point to the same suit. So for example, assuming that the first 3 cards that we select are all spades, or maybe what we want to find is 3 cards that are hearts, etc. Okay, so let's dive into the solution right away. So we have the formula of the pigeonhole principle, the ceiling of n over k equals r, and substituting the values, the number of pigeons that we have, the pigeonholes that we have is 4, and the r is 3. So in other words, what would be the n, or how many cards of n cards must be selected in order that at least r equals 3 na cards of the same suit equals 4 are chosen. Okay, so again, we must satisfy this inequality. We have the n over k, and it must be less than or equal to r and greater than r minus 1. So now, the ceiling of n over 4 must be equal to 3. Okay, and so n over 4 is less than or equal to 3, and must be greater than 2. Again, we have this restriction wherein n over k must be greater than r minus 1, but not equal to r minus 1. Okay, so we have n over 4 less than or equal to 3. It must be between here, your n over k, but not including this 2. Okay, so in order to get for us the value of n and essentially get the range of n, we just have to multiply this whole equation by 4, and we'll be left with 2 times 4 less than or equal to n. And oh no, this should be less than. Sorry. This should be less than. Okay. And that n should be less than or equal to 3 times 4. So this will result to the n should be greater than 8 and should be less than or equal to 12. Okay, so now what is the minimum number that would satisfy our equation or satisfy what we want? Okay, so we simply have to add 1 to this minimum. Okay, we just have to add 1 to this minimum and pasok na siya sa range. So essentially that is equal to k times r minus 1. So we'll multiply this part and add 1. So we have n is equal to 4 times 3 minus 1, which is equal to 2 plus 1, and that is 9. Okay, so let's have another example. How many cards must be selected to guarantee that at least 3 cards are selected? So the worst case may be that we could select all the clubs, diamonds, and spades before any hearts, and those will result to a total number of 39 selected na cards. So to guarantee that at least 3 hearts are selected, then 39 plus 3 or 42 cards should be selected. Okay, so let's have another example. Assume that a telephone number are of the form NXX, NXX, XXXX, where N here is a digit from 2 to 9, and X can be any digit. Okay, so meaning it could be from 0 to 9. Okay, so what would be the least number of area codes needed to guarantee that 25 million phone numbers can be assigned? So what we are going to find is first the total number of area codes that would be available, and we already have a given 25 million telephone numbers. So first we must find the possible number of area codes, and that is simply using counting. So we have how many possible n's are there. So since there are 8, okay, from 2 to 9, and then the x can be any digit. So we have 10 digits, 0 to 9, right? So, and then x, 10 also, and then 4 x's, so that will be 10 times 10 times 10 times 10. So this will result to 8 million. Okay, so now after that, we have k, which is at least, we have a k that is at least 4. So what we did here is we simply divided 25 million telephone numbers divided by the 8 million possible area codes. So we have at least 4. Okay, k which is at least 4.